TNPSC Combined Statistics Services Exam Unit 4. This unit is based on statistics. And so let's see what is statistical inference. Statistical inference is mainly concerned with making inferences regarding the unknown aspects of the distribution of the population based on samples taken from it. The unknown aspect may be the form of the distribution or the values of the parameters involved or both. It is true that a complete enumeration of the population will bring out all unknown aspects completely. But this involves wastage of much time and energy, and in the case of infinite populations, this is not possible. This is why we think of using samples to make inferences regarding the distribution. Methods are also developed to measure the validity of the inferences in terms of probability. Statistical inference is broadly classified into two. The first one is estimation of parameters and the second one is testing of hypothesis. Estimation deals with methods of determining numbers which may be taken as the values of the unknown parameters as well as with the determination of intervals which will contain the unknown parameters with specified probability based on the samples taken from the population. Testing of hypothesis deals with the methods for deciding either to accept or to reject the hypothesis based on samples from the population, with the degree of validity of the decision indicated in terms of probability. Now let's see what is point estimation. Any statistic, that is a function of the sample value suggested as an estimate of an unknown parameter, is called a point estimate of that parameter. Consider, for example, a normal population with unknown mean. If we suggest the mean of a random sample taken from the population as an estimate, it is a point estimate of the mean. The sample standard deviation is a point estimate of the standard deviation of the population. In general, if f of x theta is the PDF of the population where theta is the parameter, any statistic t suggested as estimate of theta is called a point estimate of theta. Evidently, a point estimate is a random variable. Note that the statistic suggested as the estimate used to be called the estimator and its value in any particular case is the estimate. A little rethinking shows that we can have any number of point estimates for an unknown parameter, as any statistic may be suggested as the point estimate. If the population is normal, we may suggest the mean, median, mode, standard deviation, third moment, or any other function of the sample values as the estimate of the population mean. Same is the case with the population variance. So we have to find which the best is. The answer of this question depends on our ideas about the desirable properties of a good estimate. According to R.A. Fisher, the father of modern statistics, the following are the most important desirable properties of a good estimate. They are unbiasedness, consistency, efficiency, and sufficiency. Let us see each of these properties in detail. The first one is unbiasedness. Let T be a statistic suggested as an estimate of a parameter theta. T is said to be an unbiased estimate of theta if expectation of T is equal to theta. Consider the possible samples of a specified size, say n, which may be taken from a given population. Corresponding to each sample, T will have a value. By saying that T is an unbiased estimate of theta, we mean that the arithmetic mean of the possible values of T is the value of theta. In other words, we mean that it is the mean of sampling distribution of T. The second property is consistency. Let Tn be a statistic where n is the sample size. Tn is said to be a consistent estimator of a parameter theta if for any two positive numbers epsilon and eta, however small they may be, a capital N can be found out such that for n greater than or equal to capital N, probability of modulus of Tn minus theta less than epsilon is greater than 1 minus eta. This idea is sometimes expressed by saying that Tn is a consistent estimator of theta if it tends in probability to theta as n tends to infinity. This means that Tn is a consistent estimate of theta. The difference between Tn and theta can be made, however small, we place in almost all samples of size small n if the sample size is sufficiently large. The definition may also be stated as Tn is a consistent estimator of theta if probability of modulus of Tn minus theta less than epsilon tends to 1 as n tends to infinity. It is to be noted that consistency is a large sample property while unbiasedness is defined for all sample sizes. A consistent estimate need not be unbiased for small samples, but it becomes unbiased as n tends to infinity. The following is a sufficient set of conditions for the consistency of an estimate, which will be found very useful in examining whether an estimate is consistent or not. If expectation of Tn is equal to theta or expectation of Tn tends to theta and variance of Tn tends to 0 as n tends to infinity, Tn is a consistent estimate of theta. The third property is efficiency. Let T1 and T2 be two unbiased estimates of a parameter. Then T1 is said to be more efficient than T2 if variance of T1 is less than variance of T2. Since the two estimates are unbiased, the arithmetic mean of the values of T1 and T2 calculated from all possible samples of size n are both equal to the true value of theta. So, if in addition variance of T1 is less than variance of T2, the concentration of the values of T1 about the true value of theta will be greater than that of T2. This is why we say that T1 is more efficient than T2. So, we may say that as variance of an estimate decreases, its efficiency increases. Variance of T2 by variance of T1 is called the relative efficiency of T2 with respect to T1, and it may be used to compare the efficiencies of estimates. The fourth property is sufficiency. An estimate of a parameter theta is called a sufficient estimate if it contains all the information about theta contained in the sample. Let T dash be any other estimate of theta and P of T dash be the joint PDF of T and T dash. Let P of T dash given T be the conditional PDF of T dash given T. If this is independent of theta, for all T dash, we say that T is a sufficient estimate. A necessary and sufficient condition for an estimate of a parameter theta to be sufficient is given by Neyman. This will be found very useful in examining whether a given estimate is sufficient for theta or not. Neyman's condition for sufficiency. Let x1, x2, etc. xn be a sample from a population with PDF f of x theta. The joint PDF of the sample, usually called the likelihood of the sample, is L of x1, x2, etc. xn theta is equal to f of x1 theta into f of x2 theta into etc. f of xn theta. T is a sufficient estimate of theta if and only if it is possible to write L of x1, x2, etc. xn theta is equal to L1 t theta into L2 of x1, x2, etc. xn, where L1 t theta is a function of t and theta alone and L2 is independent of theta.